Hi everyone, I'm Isiki from FKE UTHM. Today we'll be looking at some exercise on capacitor. So this is the questions for the cylindrical capacitors. So at the end of this video, you are able to solve this question. So let's go through the questions together. So you have a coaxial capacitor. So we know coaxial capacitor, you will have a inner conductor. Okay, so this is your inner conductor. And you also have an outer conductor. Okay, outer conductor. Okay, so it has two concentric conducting cylindrical surface. Okay, so the inner conductor has radius A and the outer conductor has the radius B as shown in the figure. So the insulator layer, is the dielectric layer that's separating the two conducting surface. Okay, so you can see from this figure, you have two dielectric media that's separating the inner conductor and also the outer conductor. And they are arranged as in the figure. Okay, so half of it is occupied by epsilon R2, okay, and half of it is occupied by epsilon R1. Okay, you can see this is how the dielectric is arranged in this cylindrical coordinate. Okay, so questions. So this is all. Okay, separating two conducting surface divided equally, half of it. Okay, so one filled with epsilon 1 and the other filled with epsilon 2. So like what I explained just now. So you are asked to develop an expression for the C in terms of L and also the given quantity in terms of B, in terms of A, in terms of epsilon 1, epsilon 2, and L. Okay, they want you to come up with the equations of C. Okay, and evaluate the value if they give you values for the A, B, epsilon 1, epsilon 2, and also the length. They want to know the value of the capacitance. Okay, so first of all, you might recall that we have derived the capacitance earlier, right? So we have derived the capacitance here. Okay, so this is the coaxial capacitor that we learned before. Okay, so after we derive, we get these equations, right? These equations. Okay, so the question is, can we use these equations in these current questions? Okay, so you have to look at the shape of the conductor. Okay, you look at the shape of the conductor. Okay, so in this case, okay, you have only, yes, you have inner and outer conductor. But in between inner and outer, you have only one dielectric medium. Okay, so maybe you will be saying, okay, if there are two dielectric medium, maybe we could do something like finding the series capacitance or parallel capacitance. But you look at the shape, okay, the shape of the capacitor, it is different. Okay, so for the previous one, okay, the shape is, you have the inner, right, and you have the outer. Okay, so this is a shape. But the shape in this question is, okay, so this is for one medium, and this is the second medium, right? Second dielectric, we break into two, okay, epsilon 1 and epsilon 2. If we look at each of it one by one, you can see the shape is different compared to the derivations earlier. Okay, so this one is a very complete circle, but this one is half of circle. So you cannot use the equation that you derive based on this case. You have to re-derive again. Okay, that's why it is very important you know how to derive the capacitance. Okay, so let's derive again. So we start from these general equations. Okay, you must remember this is a general equation for capacitance. And now we are going to look at this V. The V will be equal to negative E and dl. Okay, so this means that we have to find the E. So what is the E and how we can find it? Okay, so we can find it by using the Gauss law. So what does the Gauss law say? So the Gauss law says that the flux that is coming out from the Gaussian surface will be equal to the total charge that is enclosed by the Gaussian surface. So now let's look at our structures. Okay, if I draw it in 2D, okay, and I view this coaxial capacitor from top, okay, so you have this half of it, right, and then you have this outer conductor. So you want to find the electric field at this position in these regions. So you construct Gaussian surface here. Okay, so if the electric field is going in this way, your electric field will be in the R directions. Okay, so we can write it as epsilon E, okay, which is in the R directions. Epsilon E is because D equals to epsilon E, and multiply with the ds of cylindrical coordinate. So this one is the same like our derivations. So it will be R, d phi, dz, and this small letter r. Okay, so when coming to the interval, okay, the difference is here. Okay, so the d phi, okay, you look at this coaxial capacitor, okay, compared to the previous one. Okay, so this one is only half of a circle. Okay, so you won't integrate from 0 to 2 pi, but you will integrate from 0 to pi, and the length is L. Okay, so this is the difference. Okay, so this is the difference between the previous one and these questions. Okay, so when you do the integrations, okay, you will have epsilon E, and you will have pi, and you will have L, and you have R. Okay, R, pi, L. Okay, so this is the equations of the E. Okay, so Q divide epsilon by L R, and in the R directions. Okay, so you have find the E that could be replaced it here. Okay, the E, yeah. Okay, so we replace it into these equations. Okay, so it will be negative integrate Q over epsilon pi L R and dr. Okay, so the directions will be dr. Okay, let me put the directions. Because this is dot product, you have directions, so it's dr and r. Okay, why picking the dr? This is because, okay, your electric field is toward and in the r directions. Okay, it's in the r directions. Okay, so you cancel these things, and you are going to define the interval for your r. Okay, so look at your r. Okay, what is r? R is the distance from here, okay, towards these directions. So you'll be integrate from this point to this point. Okay, if you follow the diagram, okay, the inner conductor has a radius A and the outer conductor has a radius B. Okay, A and B is here, so you will integrate from A to B. Okay, oh no, it's not A to B. Remember, you have to integrate from negative terminal to positive terminal. So it's from B to A. Okay, B to A. Okay, so you take out those unnecessary or constants. Okay, L. And you will be focused on the integrations of 1 over R dr. Okay, so this part you are going to get epsilon by L. You are going to get ln, okay, ln R, A and B. Okay, so as a result, you get epsilon by L ln A minus ln B. Okay, so it's ln A minus ln B. Okay, so if you put this negative inside, right, inside the bracket, so it would be Q epsilon pi L ln B minus ln A. So it's ln B divided A. Okay, so this is your V. Okay, so you get your V now. Okay, where to apply your V? Okay, your V is going to be applied here. C equals to Q divide V. So you have Q multiply with the V, okay, or sorry, divide with the V. So it would be epsilon pi L over Q and ln B over A. Okay, so you cancel these things and you get your equations. Okay, for capacitor, okay, where the shape is something like this. Okay, in outer and inner. Okay, capacitor, when your capacitor shape is like this. Okay, so this will be the C. This one is not the final answer because this is a general equation when the shape of your capacitors is in this way, half of a circle. Now you have two of it. With different material. Okay, with different material. So you can see if the electric field going in this way, okay, going in this way, it means that at one time, okay, the electric field can only choose whether to propagate in material 1 or material 2. Okay, only one. So in this case, your capacitor is in the parallel configurations. Okay, it has to choose whether to propagate in epsilon 2 or whether it propagate in epsilon 1. So this is a parallel configuration. So the C total will be C1 plus C2. Okay, so what is C1? C1 is epsilon 1 pi L1 over, oh this is A, sorry, ln B over A, and plus the epsilon 2 pi L2 over ln B over A. So in fact, the L1 and L2, they are the same now. Okay, so you can just write down L. So the difference would be the material. Okay, so if you factor it, it would be epsilon naught. Okay, because it is epsilon naught, epsilon R1, epsilon naught, epsilon R2, right? Okay, pi L ln B over A, and then epsilon R1 plus epsilon R2. Okay, so this would be the capacitance of these coaxial capacitors that has two dielectric, okay, between the inner and also the outer conductor, right? Okay, so we are moving to the question B, where we have to find the capacitance, okay, given the value. Okay, so these are the value given. Okay, this one, so let me copy this one. You have to copy the value, so copy, so I paste it here. Oh, I cannot copy the things. It's okay. So let me write down what is the value. So the A is 2 millimeter, right? B is 6 millimeter, and then epsilon R1 is let me look at this one. Epsilon R1 is 2 and 4. 2. Epsilon R2 is 4, and the length is 4 millimeter. Okay, right, so this is the value. So the total capacitance would be, okay, pi L is 4 millimeter. So remember to put the milli inside the equations. And for the ln B over A, so this is 6 mm. So 6 mm, okay, over 2 mm. Okay, so the m cancel out. Okay, and then here you have R1 plus R2. Okay, so let's calculate the capacitance. So it is 6 0.07 times 10 negative 13. Okay, or 0.8. Okay, to be 0.8. Right. Okay, so this is the capacitance. Wait, so this is something wrong again about the unit, cm, right? Cm. So this one will be cm. Okay, so you have extra. Okay, so it will be 12. Okay, so this is the correct one.